Explain.
Ray tracing is one of the most important technologies behind modern computer-generated images used in movies, television, and high-end video games.
Every shadow, reflection, and highlight in a ray-traced image is the result of simulated light paths. Only rays that reach the camera matter. Simulating real light requires tracking countless interactions.
Even a single image can require billions of calculations.
Before lighting and rendering, every scene begins with simple 3D geometry created by artists. Even the smoothest surfaces are made from millions of tiny triangles.
Modern CGI scenes can contain millions of individual triangles.
Textures define color, detail, and how surfaces interact with light. Objects are carefully positioned to define scale and composition.
Material properties control reflection, absorption, and scattering.
Lights define mood, depth, and realism in a scene. Light, color, and direction change the entire mood of a scene. A virtual camera determines what the audience sees. With everything in place, the scene is ready to be rendered.
Rendering is the process of converting a 3D scene into a final 2D image.
Rendering simulates light behavior instead of simply drawing pixels. High-quality rendering can take minutes or even hours per frame. Every pixel is calculated individually during rendering.
Movies rely on offline rendering using massive computing power.
Path tracing is the most advanced form of ray tracing used today. Rays are traced from the camera to focus on visible light paths.
Path tracing finds many possible light paths through a scene. Random sampling helps approximate realistic lighting. Path tracing produces realism by accurately simulating light physics.
Each primary ray determines which object is visible at a pixel. A rendered image begins as a virtual view plane placed in front of the camera. High-resolution images contain millions of individual pixels. Primary rays are sent from the camera through each pixel into the scene. Realism comes from how light shades each surface. Surfaces facing the light appear brighter than those turned away. Shadow rays determine whether a surface point is lit or in shadow. Without lighting, ray tracing produces flat and unrealistic images. Direct illumination comes from light sources that are directly visible.
Lighting is what transforms simple geometry into believable worlds.
Shadow rays are sent toward each light source to test visibility. Once a ray hits a surface, lighting calculations begin at that exact point.
If no object blocks the path, The surface receives direct illumination.
When a shadow ray is blocked, the surface falls into shadow. Brightness depends on distance, angle, and light intensity.
Shadowed areas still receive light indirectly from the environment.
Secondary rays simulate light bouncing between surfaces. All visible light sources combine to produce direct illumination. Indirect illumination comes from light reflected off nearby surfaces.
Combining direct and indirect light creates realistic images.
Global illumination represents the combined effect of all direct and indirect light in a scene. Without global illumination, scenes appear flat and unnatural. Each bounce transfers light energy from one surface to another.
Color bleeding occurs when light reflects its surface color onto nearby objects.
Surfaces absorb some wavelengths and reflect others, spreading color.
Light often bounces several times before reaching the camera.
Even without direct light, environments remain visible due to indirect illumination.
Indirect light softens shadows and reduces harsh contrast. Multiple samples approximate accurate global illumination. Global illumination is key to photorealistic rendering. Material properties determine how light reflects, scatters, or is absorbed. Roughness controlled how sharply a surface reflects light. Rough surfaces scatter light in many directions, creating a matte look. Perfectly smooth surfaces reflect light like a mirror.
Refraction occurs when light changes direction inside transparent materials.
Transparent materials both reflect and transmit light. Metals reflect most incoming light, producing strong reflections. Non-metallic materials reflect less light and appear softer. Material properties are essential for believable rendering. Each material bends light differently based on its index of refraction. Photorealism requires simulating an enormous number of light rays. Photorealism requires simulating an enormous number of light rays.
A single frame can require billions of ray calculations. Animations multiply rendering costs by rendering every frame separately.
Modern scenes contain millions of triangles that rays must test against. Each ray must find the closest triangle it intersects. Ray tracing requires acceleration structures to remain practical.
Testing every triangle for every ray is computationally impossible.
Organizing space allows rays to ignore most of the scene. This leads to the use of bounding volume hierarchies. Bounding volume hierarchies organize geometry to speed up ray tracing. Scenes are divided into smaller bounding volumes, step by step. This process repeats until each box contains only a few triangles. Axis-aligned boxes make ray intersection calculations much faster. BVH allows rays to skip large, empty regions of space.
Rays test large bounding boxes before testing geometry.
Each ray descends the hierarchy, narrowing down possible intersections. At the lowest level, only a few triangles need to be tested.
Bounding volume hierarchies reduce millions of tests to just a few.
Only a handful of ray triangle tests are needed at the end.
Modern GPUs are specifically designed to handle the massive workload of ray tracing.
GPUs process billions of rays every second through massive parallelism.
Dedicated ray tracing cores accelerate BVH traversal and ray intersections. What once required supercomputers now fits inside a desktop GPU. Movies use ray tracing offline to achieve maximum realism. Video games use optimized ray tracing techniques for real-time performance.
Hybrid rendering balances speed and realism. Ray tracing continues to push the boundaries of realism.
Ray tracing unites physics, mathematics, and creativity.
At its core, ray tracing is the science of light.